Imagine reaching into a chaotic, unorganized drawer to pull out a single fragile light bulb without looking. For you, this is a subconscious afterthought, an invisible calculation of gravity, friction, and spatial awareness executed perfectly in milliseconds. For the most advanced machines on Earth, it is a near impossible feat of computational and mechanical mastery. The ability to intuitively interact with an unpredictable physical environment remains the ultimate unconquered frontier of synthetic intelligence. This profound capability gap is known in robotic circles as the dexterity paradox. It is a fascinating, deeply frustrating phenomenon where the cognitive tasks we find intensely difficult, like calculating complex orbital mechanics or playing grandmaster level chess, are utterly trivial for modern artificial intelligence. Conversely, the physical tasks a toddler performs effortlessly, such as walking across an uneven lawn or grasping a uniquely shaped toy, remain monumental engineering hurdles that baffle our brightest minds inside highly restricted research facilities across the globe. The race to overcome this paradox is accelerating at a breakneck pace. Elite engineering teams are pushing past the rigid limitations of traditional manufacturing robotics. They are attempting to artificially replicate the biological miracle of human locomotion and fine motor manipulation, utilizing a complex, highly synchronized symphony of titanium servos, high torque electrical actuators, and bleeding edge algorithmic code. Consider the extraordinary, highly publicized development of the Boston Dynamics Atlas. Early iterations of this bipedal machine captivated the world with astonishing displays of backflips, complex parkour routines, and synchronized dancing. These viral demonstrations showcased a breathtaking mastery of dynamic balance, explosive kinetic energy, and real-time morphological adaptation that seemed to signal the immediate arrival of a science fiction future, redefining public expectations of what a mechanical body could endure. Yet the viral spectacle masked a profound underlying fragility inherent to the system. Those impressive acrobatics were meticulously pre-programmed routines executed in highly controlled, heavily monitored laboratory environments. Every single millimeter of the terrain was previously mapped, measured, and mathematically anticipated by the engineering team, creating a closed-loop system entirely divorced from the chaotic unpredictability of the real world, where variables cannot be perfectly coded in advance. The exact moment a machine steps outside that sterile laboratory and into the unscripted reality of a human home or a bustling factory floor, those rigid mathematical models instantly shatter. A slightly misplaced rug, an unexpectedly soft piece of fruit, or a sudden minor change in ambient lighting becomes an insurmountable obstacle, paralyzing the machine in a state of absolute computational uncertainty, rendering millions of dollars of hardware entirely useless. To bridge this vast void between controlled perfection and chaotic reality, engineers are fundamentally rewriting their robotic brain. From the ground up, they are abandoning rigid, deterministic programming in favor of reinforcement learning, an advanced artificial intelligence paradigm where digital neural networks learn complex physical behaviors through millions of simulated trials, errors, and microscopic iterative adjustments, mimicking the organic learning process of a biological brain. Inside massive, cloud-based physics engines, virtual humanoids are subjected to relentless accelerated digital training. They fall over, drop objects, and fail billions of times per second in a hyperspeed simulation of reality. Slowly through brutal computational evolution, the algorithm organically discovers the optimal joint torque required to maintain balance on a shifting surface, or the precise grip strength needed to hold a delicate object without crushing it. But transferring this highly evolved simulated intelligence into a physical heavy chassis introduces a brutal phenomenon known as the reality gap. The frictionless, perfectly calculated mathematical world of a computer simulation rarely translates seamlessly to the grinding, imperfect physics of metal joints, fluctuating battery voltages, and the relentless, unpredictable pull of real-world gravity, requiring constant real-world recalibration to prevent catastrophic physical failures. Overcoming this physical friction necessitates an absolute revolution in the development of tactile sensors. Human skin is a breathtaking marvel of biological engineering, packed with millions of microscopic mechanoreceptors that instantly communicate subtle shifts in pressure, texture, vibration, and temperature directly to the central nervous system, allowing for instantaneous subconscious physical adjustments that keep a grasped object from slipping through our fingers. Replicating that localized high-resolution sensory feedback across a robotic hand requires integrating microscopic arrays of piezoresistive materials and advanced optical sensors into synthetic skin. This delicate, highly complex integration demands unprecedented leaps in material science and miniaturization, forcing engineers to build synthetic fingertips capable of feeling the microscopic slip of a glass cup long before it actually falls, processing that sensory data in fractions of a millisecond. The global economic stakes for solving this sensory deficit are absolutely astronomical. The Tesla bot, a highly publicized multi-billion-dollar initiative aimed at mass-producing an affordable general-purpose humanoid, hinges entirely on mastering this exact intersection of artificial intelligence and tactile perception. The ultimate ambition is to create a machine capable of seamlessly transitioning from assembling heavy automotive components to delicately folding household laundry, all without requiring specific reprogramming for each individual task. Leading roboticists argue that if a machine is expected to safely navigate a dynamic, unpredictable factory floor or eventually assist in intimate elder care, it cannot rely solely on visual cameras and spatial LiDAR arrays. It must possess a localized, instantaneous sense of touch to intuitively understand, map, and respect the fragile physical world it is actively manipulating, ensuring that its immense physical strength is perfectly modulated. The implications of crossing this critical engineering threshold extend far beyond mere industrial automation or supply chain efficiency. A truly general-purpose humanoid, capable of fluidly adapting to any physical environment and mastering any tool, would fundamentally sever the ancient foundational link between human physical labor and global economic productivity, ushering in an era of unprecedented mechanical abundance. This looming, inevitable reality forces a profound societal reevaluation of human purpose and economic stability. If a synthetic, tireless workforce can flawlessly execute both the complex cognitive planning and the precise physical execution of any manual task, the foundational structures of global labor markets, wage distribution, and societal purpose will face an unprecedented tectonic disruption that governments and economic institutions are currently entirely unprepared to manage. Powering these autonomous, highly capable laborers presents another formidable, deeply complex barrier to mass adoption. The biological human body operates on roughly 100 watts of energy, an astonishingly efficient metabolic engine that current chemical battery technologies cannot even begin to rival in terms of raw energy density and sustained lightweight output, highlighting the incredible efficiency of biological evolution over mechanical engineering. A bipedal machine carrying its own dense computational brain, a vast array of environmental sensors, and heavy electric motors drains conventional lithium-ion power cells in a matter of hours. This severe energetic limitation heavily restricts the utility of humanoid robots in sustained, untethered, real-world applications where constant access to a high-voltage charging station is impossible, forcing engineers to seek radical alternatives to traditional power storage. To bypass this bottleneck, researchers are actively exploring high-density solid-state batteries and novel synthetic muscles constructed from advanced electroactive polymers. These bleeding-edge smart materials contract and expand organically when exposed to electrical currents, promising to drastically reduce the energy consumption of robotic limbs while closely mirroring the fluid, highly efficient grace of biological muscle tissue, potentially extending operational runtimes from mere hours to several days. As these immense mechanical, sensory, and energetic hurdles are slowly cleared, the physical integration of humanoid robots into our daily environments will require a complete architectural and psychological adaptation from humanity. Our modern cities, domestic homes, and commercial workspaces were designed exclusively for the biological human form, not for heavy, unyielding synthetic entities, necessitating a redesign of physical infrastructure to accommodate our mechanical counterparts. Furthermore, the physical presence of a 200-pound machine moving autonomously through a crowded, unpredictable public space introduces severe, potentially catastrophic safety and liability concerns. The foundational algorithms governing their behavior must be imbued with an infallible, instantly reactive ethical framework designed to prioritize human physical preservation above all other operational mission objectives, ensuring that a simple navigational error does not result in fatal human injury. Achieving that level of absolute mathematically guaranteed behavioral safety requires real-time, edge computing processing power that borders on the miraculous. The robot must constantly perceive an unscripted environment, accurately predict the highly irrational, spontaneous actions of nearby humans, and calculate safe, evasive physical trajectories in fractions of a single millisecond, a computational load that pushes current microprocessors to their absolute thermal limit. To bridge the gap in unpredictable environments, some avant-garde laboratories are even experimenting with advanced neurotech interfaces. They are exploring whether highly trained human operators could telepresently guide these machines through the most complex, unpredictable physical scenarios, effectively lending biological intuition, moral judgment, and human adaptability to a synthetic, heavily armored frame, creating a temporary, powerful symbiosis between human consciousness and robotic durability. Ultimately, the absolute mastery of humanoid dexterity and autonomous locomotion will unlock environments entirely hostile to fragile biological life. These robust, radiation-hardened machines will become the vanguard of deep space exploration, constructing complex, pressurized habitats on the Moon and Mars, operating flawlessly in a deadly vacuum long before human astronauts ever arrive, serving as our mechanical pioneers in the darkest reaches of the solar system. The relentless multi-generational quest to build a highly functional humanoid is not merely an engineering challenge, it is a profound technological mirror held up to our own biological perfection. In trying desperately to replicate our physical form in metal and silicon, we are discovering just how incredibly complex, efficient, and elegant the human machine truly is, humbling our greatest engineers with the sheer brilliance of natural evolution. As the boundary between biological grace and synthetic capability continues to blur, we are not just building sophisticated labor-saving tools. We are actively engineering our evolutionary successors, preparing to share our physical world with a new, highly capable, metallic species born from the relentless, uncompromising crucible of human ingenuity and technological ambition, forever altering the trajectory of life on Earth.